All right, welcome everyone to the next IITE seminar. So today we have Gonzalo Robledo with us from Universidad de Chile, so from the University of Chile, and he's going to be talking to us about sensitivity and analysis of time-varying ecological systems, a topic that is close to my personal heart as well. Not that that matters, and for that reason, I will give it over to you, Gonzalo. So the floor is yours. Thank you.
Thank you very much, Professor Barabas. We are very happy and also very proud to be invited to your webinar. We will talk about, you said, sensitivity analysis of time-varying ecological networks, which means press perturbations on non-autonomous differential equations modeling ecological interactions. This work is made in collaboration with my colleagues and friends, Rodrigo Ramos-Jiliberto and Daniel Sepúlveda. Mm. Oh, Rodrigo is ecologist and he works in Universidad Mayor in the north of Santiago, and Daniel is mathematician and works in the biomathematics units in the Technological University of Santiago in the south of the city. We like to study population dynamics described by non-autonomous differential equations. Mm, Maybe, okay, it's better here. The history starts 15 years ago when Rodrigo proposed us to explain these two articles for PhD students in ecology. This article of Bender and Case about press perturbation in trophic networks and this article of Higashi and Nakajima talking about the same problem, press perturbation uh, on differential equations describing trophic interactions. This topic was hard for ecology students because involves some more advanced mathematics as implicit function theorem and notion of stability in differential equations. And the experience was very good. Uh, we learned a lot, mathematicians and ecologists. We decided to study the periodic case of this problem described by Higashi and Nakajima, and we obtained some preliminary results devoted for the omega periodic case for trophic interactions described by omega periodic systems. But when we try to extend this analysis for general time-varying networks, the problem turned impossible. And a lot of years after, in 2020, we received the visit of Christian Potche. He's a mathematician at Klagenfurt, Austria, explained us about the notion of non-autonomous dynamical systems and non-autonomous equilibrium. And we realized that with this idea, we can extend these results to the non-autonomous context. In Chile, our mathematics department gathers a team working in non-autonomous dynamics, and we realized, because the ecological department is not far, that some tools can be useful to address some problems. And currently, we are working on metapopulations models and bioprocess models. Well, I want to start with a very short review of the sensitivity analysis in the autonomous case. And I will be based in this nice book of that case. We will consider a theoretical network composed by n species interacting with each other. And a big problem is to measure the effect of the species I on the species J. We have in mind total effects, direct effects, and indirect effects. Mm, Direct effects are uh, intuitive. For example, predation has obviously a negative direct effect on the prey, but in some cases could have a positive indirect effect which is less obvious and certainly more subtle. A big problem in ecology is to neglect the indirect effects and focus exclusively to mitigate consequence of negative direct ones. Uh, so it is very important to measure total and indirect effects in a network. It seems to me that not all people have access to the slides.
Yeah, Axel, can you see
Maybe
this?
I'm just stupid. Go on. Everybody else seems to see them.
Okay.
Yeah. Got it. Got it. Thank you.
You're welcome.
Yeah, please go ahead.
Okay, so how to measure the total effects? To do it, we will consider a theoretical network described by this system of differential equation or its abbreviated form, where xi describes the abundance of the species I. We have the vector of abundance of the species, and a big important assumption will be the existence of a positive equilibrium x bar, which means that for all and each one of these functions evaluated at the equilibrium, the value is zero. We will assume that the equilibrium has the property of hyperbolicity, which means that we can compute the Jacobian metrics associated to the vector field and evaluate in the equilibrium. We compute the Jacobian here, and the hyperbolicity condition means that the eigenvalues has real part different from zero. This is the hyperbolicity condition. In addition, if the real part is negative, the equilibrium is asymptotically stable. These metrics can be written in several forms. For example, this one. This metric will be called capital A, this one B, and this one C here. And in some textbooks, this matrix capital A is denoted as community matrix. In other one is the matrix C. Anyway, if we linearize this system around this equilibrium, we will have this linear system. And the hyperbolicity condition states that by the Harman-Grobman theorem, that the dynamics of the system in a neighborhood of this equilibrium is equivalent to the dynamics of this linear system in a neighborhood of the origin. This system can be written as follows, and this constant Cig describes the direct effects of the species J on the species I. So the direct effects are more or less trivially computed under the assumption of hyperbolicity of an equilibrium, but a more complicated problem is to determine the total effects. The idea will be to consider press perturbations. We will assume that the system is at equilibrium, and we will insert small perturbations, named press perturbations, in the system. It is expected that if before we were at equilibrium, we will move to a new one equilibrium. This system can be written in this abbreviated form here. And in absence of perturbations, we recover the previous system. We can easily compute the partial derivative with respect to perturbations and compute that. Okay. I will recall this property. In absence of perturbations and evaluating in the previous equilibrium, this system is equal to zero. And we can use the implicit function theorem, which means that there exists a ball centered at the origin with a small radius, and we can define a function on this ball, and this value x star p is a new equilibrium for this system if we make short variations of the perturbation. So this function, evaluated at the origin, is the previous equilibrium, the new equilibrium. In addition, if we assume some regularity conditions of f1, f2, fn, we also can derive and obtain this identity. Now, the hyperbolicity condition implies that for small values of p, this metric is invertible, so we can obtain this identity. Now, we will make the vector of perturbations p converge to 0, and we will obtain that. And this function, evaluated at the origin, is the sensitivity matrix. Let us recall that this matrix is A, and we can deduce that the sensitivity matrix can be written in this form or in this form. We know that the community matrix describes the direct effects, but the sensitivity matrix describes the sensitivity of the species with respect to the pressure perturbations. Is Ig describes the effect of the species J on the species I. An interesting thing is that the community matrix, the direct effect matrix, is related with the sensitivity matrix. Maybe I was too fast. I will give a very short resume. We have a trophic network described by this system with an equilibrium x bar, which is hyperbolic. We linearize around the equilibrium, and we obtain this linear system. A and C are called, depending on the literature, community metrics, and describe the direct effects. If the eigenvalues of A has non-zero real part, we can deduce and construct the sensitivity matrix S as follows. And this topic is a classical topic in theoretical ecology. And our idea is how to extend this classical idea to networks described by non-autonomous differential equations. Well, so how to generalize, how to extend these ideas to the non-autonomous framework? A big problem is that we have no notion of hyperbolicity in this context, and the stability and not stability of equilibrium cannot be described by the eigenvalues. So this is a big problem. But this book, I really like this book, provides an essential notion, which is instead of work with equilibrium, work with bounded solutions on the full line, and replace the notion of hyperbolicity by the condition of exponential dichotomy. I will explain what is in some minutes. This book was very useful for us. Okay, instead of consider an autonomous system, we consider a non-autonomous system. We can see that this system is dependent explicitly of the time. By this reason, it is said that this system is non-autonomous with respect to time. It will be interesting also consider this abbreviated form. Now, as I told you, instead of consider static classical equilibria, we will work with non-autonomous equilibrium, which are functions. These functions are solutions of this system, which are bounded in the full line. Notice that any equilibrium, any classical equilibrium, satisfies these two conditions. So we are generalizing the notion of equilibrium to functions which are solution of the system and bounded in the full line. Moreover, instead of consider the hyperbolicity condition, we will consider the exponential dichotomy property. So if we have an autonomous equilibrium and we linearize around this system, we got a linear system which is non-autonomous, The exponential dichotomy is a specific property of this linear system. In some minutes, I will give a formal definition of dichotomy. But this is the main idea of our generalization. Move from equilibria to non-autonomous equilibria, and move from hyperbolicity to exponential dichotomy. Well, we have this system. Before, we assume the existence of an equilibrium. Now, we will assume the existence of a non-autonomous equilibrium, a function x bar, which is solution unbounded on the full line. And we also assume that this equilibrium, non-autonomous, is in a open bounded set omega in the positive order. As before, we will consider press perturbations, and this system can be written in this abbreviated form, where x is the vector of abundance and p is the vector of perturbations. A very technical assumption is to suppose that this function is continuous with respect to t and is C1 with respect to x and p, which means that the derivative, the partial derivatives with respect to x and p are continuous. And this is the assumption A2. Well, so in absence of perturbations, we know by assumptions that there exists a non-autonomous equilibrium x bar. What happens if we perturb the system? Can we have non-autonomous equilibriums associated to this small perturbation? Before, in the autonomous case, this was a consequence of the implicit function theorem. How to extend that? In order to extend this idea, I need to introduce some concepts. Before, I will linearize this system around the non-autonomous equilibrium x bar, and I will have this linear system. For this system, I need to construct its fundamental matrix. A fundamental matrix is a matrix whose columns are solutions of the system, and construct also the transition matrix with the fundamental matrix and its inverse. Okay. This result of Christian-Poche is very important. So, if this linear system, obtained by linearizing this one, has the property of exponential dichotomy, for any small perturbation of this nonlinear system, there will be a new non-autonomous equilibrium parametrized by the perturbation P. This family of non-autonomous equilibrium satisfy this property, which means that in absence of perturbation, we recover the previous one. And moreover, this family is differentiable and continuous with respect to the perturbation P. Okay. I never explained what is the exponential dichotomy. I will do now. A linear system has the property of exponential dichotomy if there exists a projection P and a couple of constant k and alpha such that the fundamental matrix and the transition matrix satisfy this identity. And moreover, we have these two inequalities. This identity only means that the range of this matrix is constant with respect to the time. This inequality means that the projector splits the solution in two classes, stable and unstable solutions. We can also see on this form the dichotomy splits the solution in exponential contractions and exponential expansions. By these reasons, its name is exponential dichotomy. Notice that the identity matrix is a projection. So, if P is the identity matrix, we have no expansions and only exponential contractions, and this particular case of exponential dichotomy is the well-known uniform exponential stability. This is more or less the main idea of the exponential dichotomy and emulates the hyperbolicity condition since it splits between expansions and contractions. Well, a very important result is this one. We have the network with press perturbations. We have the linearization in absence of perturbation. We can construct before the sensitivity function, the sensitivity matrix was a constant matrix. Now it's a function with matrix values described as before. We derivate x bar with respect to p, evaluate at 0, but now we have a function of matrix, and this function satisfies this non-homogeneous system, which is a matrix differential equation, where A is described by that, and B is described by that. Before, the sensitivity matrix was a fixed matrix, a constant matrix. Now it's a function with matrix values. How to prove that? By using the lemma of Christian-Poche, we know that this map is solution of this equation. As is solution, is also solution of the integral equation. We derivate with respect to p. We use the chain rule. And if we evaluate at p equals 0, this term will be st. This term will be s evaluated at t0. And this term will be s evaluated at little s. We have that. Now, recall that this term is A, this term is B, and we have this expression. Now, we derivate with respect to time, and we can see that the sensitivity matrix is solution of a differential equation. The nice thing is we have tools to solve this equation and compute the sensitivity matrix, which is the main result described here. We will assume that this linear system has an exponential dichotomy with identity as projection, which means it's uniformly exponentially stable. In this case, the sensitivity matrix, the unique sensitivity matrix, which is bounded in the full line, is described by this integral, where this matrix u t tau is this transition matrix. In addition, any other sensitivity matrix is attracted by is infinite for big values of t. The proof is very simple because we know that the sensitivity matrix is solution of this equation. The linear part has the property of exponential dichotomy, and we have a bounded perturbation. And I think of the theory of exponential dichotomy as the theory of admissibility. If the linear system has a dichotomy and the perturbation is in a space of functions, there will be a unique solution on this space of function described by this integral term. It can be proved that the unique bounded solution of this system is this one. This results back to Perron and an Uruguayan mathematician, José Luis Macer. Well, as we are considering the projector's identity, this term vanishes, and we have our sensitivity matrix. If we take other sensitivity matrix, we make this change of variables, and the stability of this linear equation implies that B converges to 0, which means that this sensitivity function is attracted for this one. And this is essentially the proof. The admissibility is quite strong because if we assume that this metric is periodic and this metric is periodic with the same period, we can prove that this solution is also a periodic matrix with the same period, which is the corollary here. In the omega periodic case, we recover the previous result, but the sensitivity matrix is periodic. As constant functions are periodic, we got the original result of that case, but we can obtain it by solving the equation using our result. It's a tricky computation, but we back to the previous result, the classical result of the autonomous case. The computations are here. If we back to the periodic case, and we recall that the sensitivity matrix is solution of this equation, we can compute its average, and we will see that the average of the sensitivity matrix satisfies this identity, where this term is the covariance between A and S infinite. I like this result because, in some sense, emulates this identity. So this is essentially our results. I have not many time, but I want to make an example with a Lotka-Volterra system. I use this book of Takeuchi, and we will consider this periodic Lotka-Volterra system where this term and these coefficients are omega periodic and continuous. Omega periodics are bounded, so we consider lower bounds and upper bounds, and if these bounds satisfies this restriction, an old result of Gopal-Samy state that if the matrix, community matrix is diagonally dominant, there exists a unique periodic solution which is attractive. So we have the main assumption, which is the existence of a non-autonomous equilibrium. The main problem is to prove that this equilibrium, if we linearize this system around the equilibrium, we need to verify the property of exponential dichotomy, which is the hardest part, the more complicated part. But fortunately, for this case, we can do it by using nice techniques from this article of Alan Laser. Following these ideas, we can prove that the system is uniformly exponentially stable, which means that the projection is the identity. And we have a sensitivity matrix, which is omega periodic. Quite fastly, I want to show this example in dimension 3. We verify the condition imposed by Gopal-Samy, and we can compute. We can see that we have a periodic solution which attracts any other solution in blue. We can compute the sensitivity matrix. We can see that in all the off-diagonal coefficients are always negative, which means that the total effects are negative. Here also, and also here. And this can be also observed by making press perturbations. This curve blue is the first species. And if we make a press perturbation in the second species, we can see that the population decreases. The same thing if we make a perturbation of the third species, the population decreases. And this situation is observed by the species number 2 and the species number 3. Now I'm finishing my presentation, but if you are interested, more details can be found in this old article and in this new article. And also, if you are interested in some results about non-autonomous dynamics, the book of William Koppel, which is the Bible of dichotomy, more modern monographies of Kleden, Rasmussen, and Christian Poche, and these articles of Alan Laser, which I like a lot these articles. Oh, I apologize for my English. My second language is French. I try to do my best. I acknowledge the Chilean Agency of Research, and obviously, I am very proud to have been invited to your seminar. I am really proud and happy. Thank you very much.
Thank you so much, Gonzalo, for the presentation and for coming to present to us. So now it will be time for questions. So if you have any questions, please raise your hand in the participant list and I will call on you. Whoa, what happened? Were some people dropped from the call? Or no, I'm just not seeing all the participants. Sorry. What? Let me fix this. Give me 1 second. For some reason, seeing
Your microphone, Gui, has gone.
I'm sorry?
Okay, your microphone was fading out then.
Oh, yeah. For some reason, I'm seeing a small subset of all the people who are in the call. But this has never happened before. This also means I might not see any hands up. Do you see any hands up?
Well, Giza is waving, but I don't know.
Yeah,
I need 8 people
I didn't. Okay.
in the call.
I don't know how to raise my hand.
It's
Yes,
changed recently because
Giza.
you have to click react and then raise hand if you want to do that now.
Yes.
It's moved.
Yes, but it doesn't seem to work. Something wrong here.
Just go ahead because
Okay, it has
strange.
worked. Okay, so what I'm surprised about this is that I used to the notion that in dynamical systems, the dynamics depends on the initial conditions. And it's obviously it is not the case in your mathematics, and I assume it is because it is start at minus infinite time. And I have a very vague idea that it replaces somehow the initial condition, but I would not mind if you explain me how to imagine this.
Oh, good question.
So why it is so that you don't need initial conditions?
Yes, it's a good question. I am not 100% able to answer, but there are a lot of things that we don't know about exponential dichotomy, but an interesting thing is the following. For example, if the system is periodic, we don't need to know the solution in the full line. We can restrict to the positive solutions. And in this context, initial conditions have a sense. Also, for the almost periodic solutions, we can be restricted to the set 0 infinite. And if we restrict to the full line, why the initial condition has no importance? A good reference is this book of Kleden and Rasmussen, which explains the notion of pullback and forward attractors, which try to explain that the omega limits are not dependent of initial conditions. Obviously, the assumption of exponential dichotomy is quite strong and is very hard to get verified. I don't know if I answered your question.
Well, obviously I don't know these things, so this is okay. I imagine that your differential equation is still that the derivative is 0 all the time. Then it has many solutions, and because if I have a initial condition, it is just remains there. But what is happening if I has the whole line, and this is the differential equation, still every constant is a solution. And then it's obviously I need some restrictions or
would it help if we would just state a very, very simple example? dx by dt equals minus x. Asymptotically, we go to 0.
Yes.
If we look over the whole line,
yeah, okay.
this will just depend on initial conditions, no matter what we do, unless there's some trick or thing that we haven't talked about.
So Axel want to ask something.
Axel, do you want to chip in on this?
Yeah,
Or?
no, I can't add anything to this, but I love the presentation, but I'm trying to get a bit more to the intuition of that. So my understanding from what you said is if we have this exponential dichotomy, if it applies, the system behaves more or less like a stable system for a stable autonomous system with some bit of wobble. And then there must be a situation where exponential dichotomy does not apply. And what would happen then? What is this thing that can go wrong? Where's the surprise suddenly?
Oh, okay. The good thing, for example, when we have exponential dichotomy, the qualitative properties of the perturbation induce the existence of a global attractor like that. If we drop this assumption, we have very few knowledge about this system. For example, the linear case, if this linear case has not an exponential dichotomy, this system can have bounded solutions, many bounded solutions. Contrarily, if we have exponential dichotomy, the unique bounded solution is the trivial one. But if we perturbate this matrix A minus lambda identity, the set of values lambda where the system has not a dichotomy is a spectrum which emulates the eigenvalues spectrum. And I agree with you. We don't know. It's a very hard topic to investigate now. But in absence of exponential dichotomy, we are in a set named spectral gaps. And it's a current topic of study. Unfortunately, I cannot give a good practical explanation.
Okay, yeah. So I thought, can you construct a system with and then another one without exponential dichotomy and explain what the difference is that you would get? Where you transition from one to the other.
Sorry, can you repeat the question, please?
If I simulate such a system,
Yes.
can I construct one example which has the exponential dichotomy and the another example has not, and I can maybe transition by changing one parameter from one situation to the other?
Yes. For example, if this metric is periodic, you can compute the flocked multipliers. If these multipliers are not in the unit circle, you will have exponential dichotomy. There exists also numerical method to detect the exponential dichotomy. We also, I forgot to say to you that we are applying the theory of exponential dichotomy for metapopulations. If you know a little bit about metapopulations, we have the colonization rates and the extinction rate. And in the scalar case, the exponential dichotomy can be described by an average. It's a good thing.
Mhm.
For example, in the scalar case, if we drop B, this system will have exponential dichotomy if this average is different from zero.
Mhm.
Maybe can be a good example. And we apply a lot this idea when studying the Levin's model of metapopulations, but with time-varying parameters.
Sorry for chipping in. It's completely connected to this. So, biologically, if we're modeling an ecological system with population densities, is it fair to say that any realistic system would respect exponential dichotomy, because to not respect it would mean something like a species flying away exponentially to infinity? And maybe taking one step further, if you study the metapopulation model, are all because the state variables are probabilities in a Levin's type metapopulation model, right? They're bounded between 0 and 1. Does this boundedness ensure exponential dichotomy or not?
Not always, but for example, in the scalar case, you can compute beyond the periodic case the Lyapunov exponents. If the Lyapunov exponents are not equal to zero, you have some chance, some probability that get an exponential dichotomy. This is in the scalar models, time varying or probabilistic models. Going beyond this situation is a good question.
Okay, but so it's not true that say in a Levin's type metapopulation model that has to be exponentially
No,
dichotomous.
no,
No, it's not.
no. Under some conditions, you can verify it, but it's the same thing when you are computing the hyperbolicity of an equilibrium.
Mhm.
It's not always hyperbolic.
No,
It's the same thing,
just
but
sorry. Apologies. Please go on.
don't worry.
Maybe I can throw in another question.
No, of course.
Yeah, you mentioned the Lyapunov exponents. Is there a simple relationship between sort of having positive Lyapunov exponents and exponential dichotomy?
Yes, absolutely. The nice example, if the scalar case,
Yes.
consider a scalar case, mm, the exponential dichotomy has associated an spectrum. This
Uh-huh.
spectrum is not a point spectrum, it's composed by intervals.
Okay.
In the scalar case, the bounds of the intervals are the Lyapunov exponents, the positive and the negative, and also the Ball exponents, which encompass the Lyapunov exponents. This topic is nicely described by Christian Poche in this monography. So there exists a strong relation between Lyapunov exponents, Ball exponents, and exponential dichotomy,
Okay.
which is
Thank you.
nicely illustrated in the scalar case. Not beyond, but there are a lot of things to do in this theory.
Mm.
So if you do, I may or may not see you raise your hand in the participant list because for some reason it's just not working for me. So just go on. Throw in your question, please.
Well, I didn't have my hand up, but I might as well ask it.
Please.
In some ways, the sort of, well, slightly, but nowhere near to this extent, mathematical ecologist question of what is the next step of getting some data sets to apply this to, or is that something that's so distant it's never really going to happen?
Currently, we are studying some metapopulation models described by, firstly, periodic and almost periodic colonization and extinction rates, and also by general non-autonomous functions. We have obtained some results emulating the classical results using some ideas of Levin's about the expected value. And we realized that the expected value of Levin's coincides with the Lyapunov and Ball exponents.
Okay.
So we applied some methods of exponential dichotomy to study the asymptotic behavior of the metapopulation models.
Did you think there's a route to apply it to, I mean, you showed some sort of food web models towards the beginning of kind of the classic indirect effects and this kind of stuff. Is there a route
Yes,
there, do you think?
the classic, but also the competition model. I forgot maybe some guy named Hallam, maybe, and Gomulkevich also, and Robert May, obviously. Yes, this one. We studied this model with almost periodic parameters of competition and exclusion. And we studied the dynamics of the model. In presence of exponential dichotomy was trivial, but in absence of dichotomy, this is a nightmare to get studied.
Okay, so there's no, it's sort of either it's quite straightforward or it's impossible. We're still kind of working out where we sit. Is that the idea? Yeah. I'll pass over to Giza. He's got his hand up.
Please go ahead.
So, if I can believe in hyperbolicity in many cases because it is just unlikely to have an exactly zero real part of the eigenvalue, except of course if there is a good reason for it. So hyperbolicity is something normal in real dynamics, I think so. Can I think in this way about exponential dichotomy, that it should be there except some non-generic case?
Yes, it's a good question. In fact, an important question in mathematics is to characterize the system where exponential dichotomy is not verified. Some people were using the theory of a French mathematician, René Berg, about in the set of linear system, the systems not verifying exponential dichotomy is of the first of second Berg category. But there are no definitive answer. But there are people working on this problem, mainly in Russia.
So, but this is some kind of general feeling or expectation. So it is. We don't have an exact proof yet, or
No,
we are absolutely unsure.
there are not yet a proof, but if you consider additional assumptions, you can prove it's a generic property.
Okay.
I have one more question. I realized, unless are there other people who have their hands up, which I cannot see. If so, please speak up. No, then I'll go ahead. So, you mentioned omega periodicity, which I'm not actually quite sure what that means, but I assume it's some sort of periodic invariant.
Oh yes, t plus omega equal t, the function. F evaluated at t plus omega equal F evaluated at
Okay.
t.
So periodic solutions. So does any of this apply to stationary non-periodic dynamics where you have an invariant set that is bounded and well-defined, but does not repeat itself?
We extended this result for the almost periodic case.
What does that mean? Sorry.
The almost periodic functions, a nice example, for example, f and g have different period. If the quotient is irrational, you got an almost periodic function, which is not periodic.
Okay, so the ratio of two periodic functions where the periods don't have an integer.
Yes.
Ratio to the so the okay, something like that. Okay, thank you. I see. So it's still okay. So it's something quite close to periodic. It feels periodic maybe, but it's not actually periodic.
Yes, I didn't put in the slides, but for example, in this case, the average is now the limit when omega tends to plus infinite, and you recover the Lyapunov exponent in the scalar case.
Oh, just the regular Lyapunov exponent.
Yes.
Okay, thank you. Questions? There are no more questions then. Thank you, Gonzalo, again for the presentation. Thanks for coming.
Thank you, Georgi.
And thank you everyone for coming. We'll be back in 2 weeks, so please stay tuned. And until then, please have a very nice rest of your day. Thank you, everyone, and bye.
Thank
Bye.
you.
Thank you very much again for your invitation.
And please send me your presentation PDF because I will link to that. Okay.
Yes.
And the video and that will be there. Okay.
Yeah.
I will do it immediately.
Thank you.
Okay. Thank you.